Welcome to Professor Explains. Settle in. Pull the blanket up to wherever feels right. Let your shoulders drop away from your ears, and let the day you have just lived begin to loosen its grip on you. There is nothing here that needs solving tonight. There is nothing to remember in the morning. There is only a long, slow walk backward into deep time and a voice to keep you company while you take it. So breathe out, all the way out, and let the room go soft at the edges. I want to begin somewhere cold, not the kind of cold you can feel through a window on a winter night, but a colder thing, a colder fact, buried so far back in the past that it makes our own winters seem like a passing mood. I want to take you to a moment about 12,900 years ago, when the world had been warming for a long time, slowly and patiently, the way a frozen house warms when you finally light the fire. The great cold of the Ice Age had loosened its hold. The enormous sheets of ice that had buried the northern half of the world were shrinking. Forests were creeping back across land that had been frozen tundra. Plants were returning, animals were returning. The whole northern world was tilting, gently and steadily, toward warmth and toward life. And then, in the middle of that recovery, with the warming already well underway, something happened that should not have been possible. The world reversed itself, not over thousands of years, not slowly. The warming did not simply pause and then change its mind across some long, gradual stretch of time. The Northern Hemisphere lurched back toward the deep cold of the Ice Age within a single human lifetime, possibly within a single decade. Picture that for a moment, or rather, let it drift through you, since picturing is hard work, and you are not here to work. Imagine a person born into a world that was getting warmer every year, a world of returning trees and softening winters, and imagine that same person, grown old, watching the cold come crawling back across the land they had known. The trees dying, the tundra returning, the familiar warmth draining out of the world as if someone had pulled a plug somewhere far away, out of sight, where no one could reach it. That is what the evidence suggests. Within the span of a life, or perhaps even faster, the world that was healing from the Ice Age fell back, hard, toward the cold it had only just begun to escape. This is the story of that reversal. It has a name, and the name is the Younger Dryas. And the strangeness of it, the thing that has kept scientists circling it for decades, is not only that it happened, but how fast it happened, and how it unhappened just as fast at the other end. The warming nearly unwarmed. The end of the Ice Age was interrupted, and nobody for a very long time could say why. Let me sit with the unknowns for a moment, because they are the heart of this whole thing, and because there is something restful in naming a mystery plainly and admitting that the answer is not simple. Nobody at first knew what could possibly reverse a warming that was already underway. Nobody knew where enough cold could come from, fast enough to undo all that recovery in a matter of years. And nobody, looking at the world's slow astronomical rhythms, the long wobble of the planet's orbit that had been gently warming everything, could find anything in those rhythms that should have flipped the world backwards so suddenly. The orbital story was a slow story, a story of tens of thousands of years. And here was a cold snap that arrived in decades. The villain, whatever it was not slow. The villain was fast, and it was hiding. So how do we even know this happened? How can anyone stand here 12,900 years later and say with any confidence that the world lurched back toward cold within a human lifetime? You cannot dig up a thermometer from that long ago. There were no records, no writing, no one keeping the temperature. And here is where the story turns elegant, where it becomes one of those quiet detective tales that the deep past sometimes hands us, almost as a gift. It begins with a flower. There is a small Arctic alpine flower called Dryas octopetala, the mountain avens. It is a low, hardy, white-petaled thing, the kind of plant that hugs the ground in places too cold and too harsh for most other living things to bother with. It grows in tundra. It grows in the high, exposed places where the wind never really stops and the soil is thin and the summers are short. It is a flower that belongs to the cold. And like every flowering plant, it releases pollen, fine and dust-like, drifting on the wind. Some of that pollen then, as now, settled onto the surface of lakes and ponds and slowly sank year after year, season after season, down through the still water and into the soft mud at the bottom. Now here is the lovely part. Lake mud, undisturbed, builds up in layers slowly, patiently, the way dust gathers on a shelf no one ever touches. Each layer is a little slice of a year or of a season sealed beneath the one that came after it. The pollen that fell into the lake gets trapped in that mud and stays there, preserved, for thousands upon thousands of years. And pollen is tough. The outer shell of a pollen grain is one of the most durable things a plant ever makes, and it keeps its shape, its little sculpted fingerprint, long after the flower that released it has crumbled to nothing. So if you carefully sink a hollow tube down into the bottom of an old European lake and pull up a long, undisturbed core of that layered mud, you are pulling up a calendar, a record, a long, dark ribbon of time, with the youngest mud at the top and the oldest mud far down at the bottom. And when scientists pulled up those cores from lakes across Europe and looked layer by layer at what kind of pollen was sealed inside, they found something that told a story all on its own. In the deeper, older layers from the heart of the Ice Age, there was a great deal of pollen from cold-loving tundra plants, including the mountain avens. Then moving upward into younger layers, the cold plant pollen faded, and the pollen of trees and warmth-loving plants took over, the signature of a warming world, of forests returning, of the Ice Age letting go, the recovery written in pollen. And then higher still, in layers younger than that, something unexpected. The tree pollen retreated, and the pollen of the cold-loving plants came back. The mountain avens returned. Dryas octopetala, that small white Arctic flower, reappeared in abundance in the lake mud, blooming again across land that had only recently grown warm enough for forests. The flower came back. And the flower coming back meant the cold had come back. The tundra had returned to places that had begun to forest over. The warming had reversed, and the proof of it was sitting there in the mud, in the pollen of a cold-tolerant flower, returning to lake beds where it had no business growing again. This is how the period was first recognized. This is where the name comes from. The Younger Dryas is named after a flower, after Dryas octopetala, after the pollen of a small Arctic bloom buried in European lake mud, telling us, across all those thousands of years, that the world had grown cold again. I find something deeply restful in that, and I hope you do too. The idea that the answer to how cold a forgotten world was 13,000 years ago was waiting quietly at the bottom of a lake, written in flower dust. That a thing so small and so soft could keep a secret so large for so long. The mud held it. The cold flower bloomed in the layers, and then it was red. And the reading told us that the warmth had failed. Before we go any deeper, let me do a small thing, the kind of small human thing that makes a long night feel less lonely. I would genuinely like to know where in the world you are listening from tonight. The comments are there, and I do read them. And there is something quietly companionable about imagining all the different windows, all the different dark rooms, all the different corners of the world where someone is lying still and listening to this same slow story at the same time. So if you feel moved to, leave a note and tell me where you are. And if you are new here and you find that this slow and careful kind of journey helps you towards sleep. You are welcome to subscribe so that more of these can find their way to you on other nights when sleep is slow in coming. That is all. No urgency. We will not speak of it again until the very end, if at all. The rest of this night belongs to the cold and the ice and the long, strange story of a warming that nearly unhappened, because tonight we are going into it. Slowly, all the way down. We are going to walk, step by step, into the question of how a warming world reversed itself, where the cold came from, why it arrived so fast and left even faster, and why, after all these years, the smartest people who study it still cannot fully agree on every part of it. There may be no neat answer waiting at the bottom. In fact, there is not entirely, and that is part of the wonder of it, not a flaw in it. You are allowed to drift off anywhere along the way. You do not need to reach the end. The end will keep. The story will still be here, and the cold flower in the mud will still be blooming in those layers, whether you are awake to hear about it or not. So let me set the frame properly, gently, the way you lay out the pieces of a thing before you begin. Let me give you the shape of the deep time we are wandering into, so that the names to come have a place to rest. Go back, then, to the depth of the cold. There was a time, the coldest stretch of the long ice age, that scientists call the last glacial maximum. The maximum of the glaciers, the fullest extent of the ice. This was the world at its most frozen, when the great ice sheets reached their greatest size, when so much of the planet's water was locked up in ice that the seas themselves were lower, and the northern lands lay buried beneath sheets of ice that were, in places, miles thick. It is hard to hold that in the mind. Miles of ice, whole landscapes, whole future cities, future forests, all of it pressed flat beneath a weight of frozen water so vast it bent the very crust of the earth downward. This was the cold the world had to climb out of. This was the bottom of the long winter, the last glacial maximum. Hold that as the floor of our story, the deepest cold, the place the world began its long, slow climb away from. And then the climb began. The world started to warm. The orbital rhythms, the slow wobble and tilt of the planet's path around the sun, shifted the sunlight in ways that nudged the world toward thaw, and the great ice sheets began, ever so slowly, to give ground. This was not quick. This was the patient warming of tens of thousands of years, the kind of change too slow for any single creature to notice, the kind that only shows itself across the long span of generations and generations. But it was real, and it was steady, and it carried the world up out of the deepest cold. But the climb was not a smooth one. It was not a single, clean line from frozen to warm. The world stuttered on its way up. It lurched and paused and fell back, and recovered again and again, like someone climbing a long stair in the dark, sometimes finding the next step, sometimes stumbling back down to the one below. And those stumbles, those falls back toward cold in the middle of the warming, left their own marks in the lake mud, their own returning waves of cold flower pollen. There was an early one that scientists call the oldest Dryas, and there was a later one they call the Younger Dryas, each one a cold reversal, a falling back, written in the same mud by the same cold-loving plants, returning when the warmth failed. Oldest Dryas, Younger Dryas. The names are plain, almost stubbornly plain, naming each return of the cold flower by its place in the order of time. And between these cold stumbles came the warmth, the good spells, the steps up the stair. The most important of these for our story is the warm interval that came just before the great cold reversal we are following tonight. It is called the Berling-Allerud Interstadial. Let me unfold that name a little because it sounds more forbidding than it is, An interstadial is simply a warm spell sitting between colder ones, a window of warmth within a longer cold age, the way a mild bright afternoon can sit in the middle of a hard winter week. The Bulling Alarud was such a window, and a generous one. During this warm interval, the world really did seem to be recovering. The ice was retreating, forests were spreading north into Europe, reclaiming land that had been frozen tundra. The cold-loving plants, the mountain avens among them, were retreating to the high, cold corners where they could still survive, pushed back by the returning trees. Animals followed the forests. The warmth seemed to be winning at last. The world, after the long agony of the last glacial maximum, after the false starts of the oldest and older Dryas, finally seemed to be settling into a real and lasting thaw. That is the moment to hold in your mind as you drift. A world warming, forests returning, the Bulling Alarud interstadial, a long warm window, the recovery well underway, the worst of the Ice Age seemingly behind, everything pointing toward warmth, everything pointing toward the world we would eventually come to know, the end of the Ice Age in sight at last. And then the Younger Dryas. Out of that warmth, out of that recovery, came the cold reversal we have been circling all this time, the youngest and the most pronounced of all those Dryas cold returns, the most dramatic falling back of them all. Roughly 12,900 years ago, in the middle of the Bulling Alarud's warmth, the world plunged back toward the cold. The mountain avens bloomed again in the lake mud across Europe. The tundra returned to the recently forested land, and it lasted, this cold, not for a season, and not for a handful of years, but for well over 1,000 years. From around 12,900 years ago to around 11,700 years ago, the Younger Dryas held the Northern Hemisphere in its grip, a long, cold interruption sitting right in the middle of the end of the Ice Age, a stretch of more than a millennium when the warming that should have carried the world into its new warm age simply stopped and reversed, and the cold came back to stay a while, the youngest of the Dryas, the most pronounced, the deepest of the stumbles on that long climb up the stair. After the warm Bulling Alarud, after the recovery had seemed all but certain, the world fell back, and it fell back fast, and it stayed cold for over 1,000 years. Let me linger on that span, 12,900 to 11,700 years before the present, because the numbers matter, and the numbers are also, in their own quiet way, soothing to say slowly. More than 1,000 years of returned cold, more than 1,000 years in which the world that had been warming held its breath and stayed frozen at its northern edges. That is longer than all of recorded human history, longer than the span from the building of the oldest cities you can name down to this very night. An entire age of cold sitting inside the end of the Ice Age, opened by a reversal so fast it may have taken only a decade, and closed, as we will come to much later, by a re-warming faster still. A cold age with abrupt walls at both ends. That is the Younger Dryas. That is the strange, sharp-edged thing we are walking into. And here, before we go on, is the part that I think makes this whole story worth lying awake just a little longer for, or worth drifting into sleep upon, whichever the night decides. The deepest mystery is not simply that the world got cold. Worlds get cold. The Ice Age was a long lesson in how cold a world can get. The mystery is the speed. The whole long story of the Ice Age, the building and melting of those mile-thick sheets, was a slow story governed by the slow rhythms of the planet's orbit, unfolding across tens of thousands of years. That was the tempo the world was supposed to move at. Slow, patient, glacial in every sense of that word. And then the Younger Dryas arrived and broke the tempo entirely, It came on in decades, not millennia. It reversed in a human lifetime a warming that had taken thousands of years to build. And whatever caused it, whatever villain was hiding out of sight, it was something fast. Something that could flip the world from one state to another almost overnight in the long reckoning of geology. Something that did not wait for the slow orbital rhythms at all. That is the puzzle that has held scientists for decades. The slow story cannot explain a fast event. The orbit was warming the world gently over the long haul. It had no sudden reversal to offer. So something else, something quicker and stranger, had to reach in and flip the switch. And the question of what could possibly do that, what could chill the Northern Hemisphere within a lifetime in the middle of a recovery, is the question we will spend this long night slowly, gently turning over. There is an answer that most who study this now believe, and it is a beautiful, almost unsettling answer, because the most likely villain in this story is not some outside force at all. The most likely culprit is the warming itself. The most likely culprit is the planet's own meltwater, the very water freed by the thaw, turning against the world that freed it and helping to drag it back toward the cold. But we are getting ahead of ourselves, and there is no need to hurry. That thread we will pick up slowly later when we follow the water down into the ocean and see how a flood of fresh, cold water can reach into the sea and switch off the great current that carries warmth to the north. For now, let the frame be enough. Let the shape of it settle over you like the blanket you are already under. There was the deepest cold, the last glacial maximum, the bottom of the long winter, miles of ice pressing the land flat. There was the slow climb up out of it, warming over tens of thousands of years, stuttering and falling back in cold reversals named the oldest Dryas and the older Dryas. There was the long, warm window of the Belling-Alarud interstadial, when forests returned and the world seemed at last to be truly healing. And then there was the Younger Dryas, the youngest and the most pronounced of all the cold returns, falling out of that warmth roughly 12,900 years ago, possibly within a single decade, holding the Northern Hemisphere in cold for over 1,000 years until around 11,700 years ago, an entire age of cold with sharp and sudden walls at both ends. And all of it, the whole great fact of it, first read by us in the soft mud at the bottom of European lakes, in the returning pollen of a small white Arctic flower, the mountain avens, Dryas octopetala, blooming again in the cold layers and giving the whole period its name. A flower as the witness, flower dust as the testimony, the bottom of a lake as the archive that kept it all safe across 13,000 years until someone came with a hollow tube and the patience to read it. There is a kind of comfort in the idea that the earth keeps such careful records of itself, even of the things no one was there to see. The mud remembers. The ice remembers, as we will find. The earth lays down its layers year on year, season on season, and seals each moment beneath the next, and waits with infinite patience for someone to come and read it back. The cold of 13,000 years ago is not gone. It is filed away in the flower dust and the frozen layers, in places dark and still and undisturbed, holding their shape, keeping their secret, until they are gently lifted into the light and asked, what was the world like then when the warming failed? We will be asking that question all night. We will follow the cold down into its causes. We will find the instruments, the ice cores far to the north, that let us count the very years of the event almost one by one. We will follow the water, the meltwater, the planet's own thaw, down into the great currents of the ocean to find out how a flood of fresh water could reach into the sea and silence the engine that warms the north. We will find the lake that may have broken its banks. We will see why the cold fell so unevenly across the world, biting hardest in the north and the Atlantic, and doing something stranger, almost the opposite, far to the south. We will meet the great vanished animals of that age, the mammoths and the mastodons and the others, and ask, carefully and without rushing to blame, what the cold had to do with their passing. And we will come, much later, to a genuine and still unsettled argument, a real scientific dispute about whether something fell from the sky and helped to start it all, an idea we will hold honestly, neither as proven fact nor as foolishness, but as the open question it truly remains. But none of that is for now. For now, you have done the work of arriving. You have come all the way back to the edge of the deep cold, and you are standing gently at the lip of the Younger Dryas, looking down into more than 1,000 years of returned winter, with a small white flower blooming in the mud at your feet to mark the way. That is enough for one stretch of the journey. Let your breathing slow to match the slowness of the mud, layer settling on layer, year sealing over year. Let the warmth of your own room, your own bed, hold you while we wander together through a world that lost its warmth so long ago. There is no cold here that can reach you. The frost we are speaking of melted 12,000 years before you were born. You are only visiting it gently from somewhere safe and dark and quiet, and you may leave whenever sleep decides to take you. So rest there for a moment at the edge of the cold with the flower in the mud and the long age of returned winter spread out below. The story holds steady. It is not going anywhere. And when you are ready, when your breath has slowed and the room has gone soft and the names have all settled into their places, we will take the next slow step down toward the ice that counted the years and the great current of the sea that the cold reached in and stilled. There is a particular kind of patience required to read the past, and it is not the patience of waiting for documents to be translated or archives to be opened. It is something far older and more physical than that. It is the patience of standing in a cold room, in a laboratory somewhere in Greenland or Denmark, with a cylinder of ice stretched out before you, on a table, lit from below so that it glows a faint blue-white like something still alive, and reading it the way a careful reader reads a book whose pages are not made of paper but of years. The cylinders come from deep beneath the surface of the Greenland ice sheet, extracted through a process so painstaking and so methodical that it seems almost ceremonial. A drill presses down through the accumulated snowfall of thousands of winters, turning slowly, pulling the ice up in sections, each section a fragment of time sealed inside a column no wider than your forearm. The names of the major cores are not poetic names. They are practical ones carrying the coordinates and the institutional history of the teams who pulled them. GISP-2, GRIP, NGRIP. The Greenland Ice Sheet, Project 2, the Greenland Ice Core Project, the North Greenland Ice Core Project. Separate endeavours, separate drilling sites, conducted across roughly the last half-century by separate international teams, all asking the same question through different cylinders: what happened up here, year by year, going back through time? And the ice answers. That is the remarkable thing, the thing that still feels slightly improbable, even when you understand the mechanism. Every winter in Greenland, snow falls and compresses. Every summer, the surface melts slightly or evaporates in a slightly different way, leaving a faint seasonal signature in the crystal structure of what will become, in time, another thin layer of ice. If you look carefully enough at a cross-section of Greenland ice, you can see these layers the way you can see the rings inside a felled tree, except that instead of telling you about wet years and dry years in one forest, they are telling you about something far larger, the global atmosphere. At the moment, each layer was sealed. The dust content changes. The ratio of certain oxygen isotopes, the ones designated 16O and 18O, shifts in proportion to the temperature at the time the water vapor formed, because heavier molecules condense and fall closer to home in cold conditions, while lighter ones travel farther before falling as snow at the poles. So the oxygen in each layer is a small thermometer, a reading of the atmospheric temperature preserved in a form that can still be measured many thousands of years later. The accumulation rate changes too. In very cold periods, less snow falls over Greenland, so the annual layers are thinner. In warmer periods, they swell. The dust content spikes during cold, dry, windy periods when the continents are exposed and bare. The chemistry of the bubbles trapped within the ice, tiny pockets of the ancient atmosphere itself, sealed there at the moment the snow compacted into ice, records the composition of the air. All of it, year after year, layer after layer, stacked into a single vertical column that the drill pulls up section by section and lays out for reading. What the cores from GISP2 and NGRIP and GRIP recorded, when they reached the layers corresponding to roughly 12,900 years ago, was the signature of the cold arriving. In the oxygen isotope ratios, a shift downward toward the lighter isotope, toward the signal of cold. In the dust record, an increase, the dried-out continents sending their particles into an atmosphere that had turned drier and more vigorous with wind. In the accumulation layers, a thinning, less snow, reaching the ice sheet each year as the cold suppressed the evaporation and the atmospheric circulation changed. And then for more than 1,000 years, the cold signal holds, locked in place, layer after sealed layer, the way a door holds shut when the latch has caught. And then it ends, and the ending is the thing that stops you, that makes you set down whatever you are carrying and simply stare at the column of ice. The ending of the Younger Dryas in the Greenland record is not a gradual resumption of warmth, not a slow, gentle brightening of the oxygen ratios back toward the signal of a warmer world. The NGRIP core places the termination of the Younger Dryas at approximately 11,700 years ago, and what the core records at that boundary is not a gradual change. The temperature over Greenland read through those oxygen isotopes and the accumulation layers and the dust signal and everything else the ice holds rose on the order of 10 degrees Celsius over a span of time estimated at roughly a decade, perhaps a few decades at most. Some of the proxy measurements suggest the transition was even sharper in certain indicators. Not a century, not a millennium, a decade, maybe 10 winters, maybe 20, maybe 30, but nowhere near the span of a human lifetime. That is, for any intuition built around the way the modern world changes, nearly incomprehensible. 10 degrees of warming in a decade is not a small adjustment. For comparison, the difference in average temperature between the last glacial maximum, the coldest deep point of the Ice Age, and the relatively warm and stable Holocene that followed is estimated at somewhere between 4 and 7 degrees Celsius globally, with much larger regional changes in high latitudes. The warming from the depth of the last Ice Age to our current warmth took roughly 10,000 years to fully establish itself, a long, slow climb with interruptions. And then at the end of the Younger Dryas, something comparable to that entire journey was compressed into a single decade over Greenland. The isotopes lurch upward, the dust drops away. The accumulation layers thicken almost immediately as the warmer atmosphere carries more moisture and delivers more snow. The transition is, in the record, nearly instantaneous. This is not a metaphor or an interpretation. It is what the layers show, as measured independently by multiple teams, corroborated across multiple cores, drilled at different locations on the same ice sheet, and cross-checked against other archives around the world. The NGRIP core is particularly important here because it provides the formally ratified chronology. The International Commission on Stratigraphy, the body responsible for defining the official divisions of geological time, has placed the base of the Holocene epoch, the epoch in which all of recorded human history takes place, at 11,700 years before present, plus or minus 99 years, and has designated a specific section of the N-grip ice core as the official reference point for that boundary. A specific depth in a specific cylinder of Greenland ice, housed and measured and formally agreed upon, is the bottom of our current geological chapter. What came before it, going down deeper into the ice, is the Pleistocene. What began above it is the Holocene, and the layer that separates them is the moment the Younger Dryas ended. So the cold that we have been walking toward, this returned winter that settled over the Northern Hemisphere 12,900 years ago, is not some obscure ancient episode buried too deep in time to find precise edges. It is bounded with precision at both ends by the abrupt onset roughly 12,900 years before the present, and by the terminus at 11,700 years before the present, ratified in ice, confirmed in annual layers, and placed as the formal beginning of our own geological era. Every year of recorded history, every civilization, every invention and war and harvest and migration that humans have undergone since the first cities were built along the river valleys of the ancient world, has taken place within the Holocene. And the Holocene begins at the moment this cold ended. But the cold itself, the Younger Dryas, does not exist in isolation in the record. The ice cores go deeper than 11,700 years. They go back through the Bølling-Allerud, that warm pulse that preceded the cold, where the oxygen isotopes brighten and the dust falls away, and the world was, for a time, recovering well. And deeper still through the oldest and older Dryas cold phases that punctuated even earlier periods. And deeper still, back toward the last glacial maximum, all of it held in the ice year after year, in layers that require a kind of sustained attention to read correctly, a refusal to leap past the complexity of what is actually recorded there towards some simpler story. What is actually recorded there, above all else, is that the climate system of this planet is not a smoothly operating machine that moves only slowly and in straight lines. It is a system with thresholds. It can flip. It has flipped with extraordinary speed, multiple times in the ice record. The Younger Dryas is simply the most recent and most sharply recorded of these transitions. It is the one closest to us in time, the one whose layers are still thick enough and well preserved enough to be read at annual resolution, the one whose consequences reached the human world directly. But the character it reveals in the climate system, the possibility of a rapid state change, a near instantaneous reorganization of how heat moves around the planet, is not unique to this one event. It is something the ice has been quietly showing us for decades, in column after column of frozen time. The question that all of this naturally raises, the question that makes the Younger Dryas more than a curiosity and turns it into a genuine mystery, is the same question that has been sitting quietly here since the beginning. What caused it? What mechanism was powerful enough to reverse a warming that was already well underway, to take a world that had been climbing toward the relatively stable temperatures of the Holocene and push it back decisively into more than 1,000 years of near-glacial cold, and then, when it had run its course, release its grip so suddenly that Greenland warmed 10 degrees in roughly a decade? The answer that the evidence most strongly supports, the one that has earned the widest acceptance among paleoclimate researchers who have spent careers examining the period, is one that requires a small act of imagination to feel properly. Not much imagination. The physics is not exotic, but it requires holding in your mind a picture of how heat moves across the surface of this planet, and then imagining what happens when that movement is interrupted. The Atlantic Ocean is not a still body of water. It is, among other things, a vast conveyor belt, a slow circulation of water driven partly by temperature and partly by salt, driven, in the technical language, by the contrasts in density that temperature and salinity together produce. Warm water is less dense than cold water. Fresh water is less dense than salt water. When surface water at high latitudes in the North Atlantic is exposed to cold air over a sufficient period, it cools, and as it cools, it becomes denser, and eventually dense enough to sink. It sinks from the surface down toward the deep ocean, and in doing so, it pulls more surface water northward from lower latitudes to replace it, and that surface water carries the warmth of the tropical Atlantic with it as it travels north. The Gulf Stream is the most famous part of this system, the warm current that moves along the eastern coast of North America and then crosses the Atlantic as the North Atlantic Drift, carrying heat northward toward Europe and the higher latitudes. And the deep sinking of dense cold water in the North Atlantic is the engine that sustains this northward movement at the surface. The formal name for the whole of this circulatory system, the surface currents moving warm water north and the deep return flow carrying cold water south at depth, is the Atlantic Meridional Overturning Circulation, abbreviated AMOC. It is a description of one of the fundamental ways the planet distributes heat. Without it, the high latitudes of the North Atlantic Basin would be considerably colder than they are, deprived of the continuous supply of tropical warmth that the surface current brings. The mild climate of northwestern Europe, the fact that cities at the same latitude as Hudson Bay and Siberia can remain temperate and navigable year-round, is substantially a consequence of the AMOC delivering heat that those latitudes would not otherwise receive. Now hold the image of this conveyor steady and introduce something new into it. Introduce a very large quantity of fresh water arriving suddenly at the surface of the North Atlantic. Water with almost no salt in it, carrying almost no of the dissolved mineral that makes seawater heavy. Fresh water is markedly less dense than salt water, and when it arrives at the surface in large quantities, it forms a buoyant layer that resists sinking, a layer that will not go down. And if the surface water in the deep water formation zones of the North Atlantic will not sink because it is no longer dense enough, the engine of the AMOC begins to weaken. The pull that draws warm surface water northward from the tropics slackens. Less warm water arrives from the south to replace the sinking. The northward transport of tropical heat diminishes or stops altogether, and the North Atlantic and its surrounding regions, deprived of that transported warmth, cool. They cool rapidly because it is not that they have had their heat source slowly dimmed, but that it has been turned off, replaced by the insulating blanket of fresh water sitting light and cold on the surface, refusing to do the work of sinking that normally drives the whole circulation. This is the mechanism. This is what the evidence most strongly points to as the proximate cause of the Younger Dryas cooling, a massive and rapid influx of fresh water into the North Atlantic, reducing surface salinity, suppressing the density contrast that drives deep water formation, weakening or shutting down the AMOC, and thereby cutting off the supply of tropical heat that the Northern Hemisphere had been receiving, just as the world was recovering and warming from the last glacial maximum. You can feel the elegance of it and the horror of it simultaneously. The world was warming, the warming was melting the ice sheets, and the melting ice sheets were releasing fresh water, the planet's own meltwater, into the very ocean that needed to be salty and cold and dense to keep the heat moving northward. The process of recovery was producing the very substance that would interrupt the recovery. The ice, in melting, was releasing the water that would cool the ocean, that would cool the air, that would encourage the ice to stop melting. A kind of vast, slow self-interference, a planetary negative feedback operating on a 1,000-year timescale, swung into motion not by any external force, but by the internal dynamics of the ice and ocean system responding to their own changing conditions. The analogy that brings the salinity physics closest to something you can feel without a laboratory is the oil and water in a salad dressing left to sit. Fresh water, like the oil, prefers to stay at the top. It does not want to mix and sink. Salt water, denser and heavier, would normally provide the layering that fresh water needs to be pushed below. And in the normal operation of the North Atlantic, the cold air at high latitudes takes care of the sinking by cooling the already salty surface water until it is dense enough to drop. But pour enough fresh water onto the surface, and the salt concentration drops below what cold air alone can compensate for. The water cools but will not sink. The engine stalls. The difference of a few parts per thousand in salinity, a change that would be imperceptible to taste, something between the saltiness of a teardrop and the saltiness of a glass of tap water, is enough to alter whether or not the North Atlantic surface water will sink at a given temperature. Density is exquisitely sensitive to both temperature and salinity, and the deep water formation regions of the North Atlantic operate near enough to their threshold that a significant freshwater input can push them across the boundary between sinking and not sinking. The ocean circulation that keeps a hemisphere warm is, in this sense, much more precarious than its enormity would suggest. It is a system of considerable strength running at a relatively narrow margin. And the ice core record, those oxygen isotope ratios and dust layers and accumulation rates preserved in the Greenland cylinders, shows what happened to the climate of the North Atlantic basin when that margin was crossed. It shows the temperature signal dropping within decades, the dust thickening as the continents dried, the accumulation thinning as the cold reduced the moisture-carrying capacity of the atmosphere over Greenland. It shows the cold holding for more than 1,000 years, sustained through layer after annual layer, with no drift back toward warmth, no gradual softening. And then it shows the ending, the abrupt, nearly instantaneous resumption of the warmer signal that defines the beginning of the Holocene, when, for reasons the evidence also addresses, though not yet completely, the fresh water stopped arriving, or dispersed, or the amok rebuilt its strength, and the conveyor began moving again, and the tropical heat returned to the North Atlantic, and Greenland warmed 10 degrees in something like a decade. The ice cores are the most precise recording instruments we have for the Younger Dryas, but they are not the only ones. Ocean sediment cores from the North Atlantic basin carry their own signatures, changes in the species of foraminifera, tiny shelled marine organisms whose species composition is sensitive to water temperature, buried in the sediment in layers that can be dated and read. The cooling of the North Atlantic surface water during the Younger Dryas is visible in these sediment records as a shift in species assemblages, the cold water organisms becoming dominant in layers that correspond to the same period the ice cores record the cold air above. The two archives, ice above, sediment below, tell the same story through entirely different proxies, through different organisms responding to different physical properties of the climate, which is what makes the story convincing beyond any single measurement system. Pollen records in European lake sediments tell the same story from the land. The tundra plants came back, the birch forests that had begun to colonize southern Scandinavia and the British Isles during the preceding warm period, contracted or disappeared, replaced again by the pollen signatures of the cold-tolerant plants, the Dryas octopetala prominent among them, the small white flower that gave the whole period its name. Those European lake sediments show the return of tundra conditions in regions that had been well on their way to forested landscapes, and then, at the termination, another shift back toward birch and eventually toward the diverse mixed forests of the Holocene as the warmth came back and the trees followed it northward again. All of these records are saying the same thing through flowers and marine organisms and oxygen isotopes and dust and sea ice and the chemistry of ancient air. The amok weakened, the North Atlantic cooled, the cold spread outward from that ocean across the surrounding land, and then the circulation resumed and the warmth returned. The mechanism that connects these observations, fresh water, suppressing deep water formation, weakening the overturning circulation, cutting the heat transport, is not speculative. It is supported by the physics of seawater density, by models that reproduce the behavior when the appropriate freshwater forcing is applied, by the geographic pattern of the cooling, which is strongest close to the North Atlantic and attenuates with distance from it in a way consistent with the loss of a heat source centered on that ocean, and by the other evidence we will come to shortly, the evidence about where the fresh water came from. But for the moment, hold the picture that the ice cores have built, a drilling crew, far out on the Greenland ice sheet, in a structure that keeps the wind out but not entirely the cold, pulling up sections of ancient time from a hole in the ice, laying them out under fluorescent lights, and reading in the layers the memory of what happened to this planet nearly 13,000 years ago. The warming that had been building for millennia interrupted. The cold that settled in and held, the patience of more than 1,000 winters sealed into crystal, into dust, into the bodies of molecules that carry the weight of their history in the ratio of their atoms. And then the ending, sharp as a door, opening into a warm room, bright as the sudden swing of temperature in the oxygen record, recorded there in the ice as though the world decided one decade to simply stop being cold and declined to explain itself. That abruptness at both the onset and the termination is what the ice cores have added most decisively to our understanding of this period. Before the era of ice core research, before the annual layer counting became possible and the chronologies became as precise as they now are, the Younger Dryas was known from pollen records and ocean sediments, but its speed was not known with anything close to the precision those archives provide. Pollen in a lake sediment accumulates on timescales of decades to centuries at best. It can tell you the cold returned and the tundra plants came back, but it cannot tell you whether that transition took 10 years or 200. The ice cores can, within the limits of the annual layer resolution, which is to say, within the span of a decade or two. And what they tell you is that the transitions at both ends of the Younger Dryas are not gentle ramps or gradual blending, they are steps, thresholds crossed, before and after, with almost nothing in between. This is what paleoclimate scientists mean when they speak of the Younger Dryas as the paradigm case of abrupt climate change. Not merely that it was a cold period, not merely that it interrupted a warming trend, but that it began abruptly and ended even more abruptly, and that the beginning and the ending were both associated with changes in the Atlantic circulation that happened on timescales far shorter than the astronomical cycles, the slow wobbles of the Earth's orbit and tilt that drive the long pacing of the ice ages. The Milankovitch cycles that set the broad rhythm of glacial and interglacial periods operate on time scales of tens of thousands to hundreds of thousands of years. The Younger Dryas fits within that rhythm in the sense that it occurred during the transition from the last glacial period to the current interglacial, but its abruptness cannot be explained by the smooth, slow changes in incoming solar radiation that the orbital cycles produce. Something faster was at work, something capable of reorganizing the climate of a hemisphere within a human lifetime and of releasing it again within a decade. That something, the evidence argues, was the ocean, specifically the Atlantic Meridional overturning circulation, sensitive to salinity and temperature at the surface of the North Atlantic, sitting close enough to its own threshold that a sufficient perturbation of its fresh salt balance could flip it from one operating mode to another and back again in spans of time that, on geological scales, are nearly instantaneous. The epoch as a threshold system, not a smooth dial but a switch, on carrying tropical heat to the high latitudes, keeping the North Atlantic mild and the Northern Hemisphere on its recovery trajectory, and off, or severely weakened, starving those same latitudes of their heat supply and returning them to conditions not unlike the deep cold of the last glacial maximum, at least in their northern reaches, at least in terms of the temperatures the atmosphere reached in the worst of the winters that followed. The ice cores gave us the precision to know how fast. The physics of deep water formation gave us the mechanism by which it could be so fast. And between these two, the general outlines of the Younger Dryas became clear. Not a mysterious anomaly requiring some special or exotic explanation, but a predictable, in retrospect, consequence of a freshwater-sensitive circulation operating in a world where vast quantities of fresh water were available in the form of ice, and that ice was melting. The question that remains, and that the next movement of this story will take up, is where precisely that fresh water came from, in what quantity, through what path, and into what part of the ocean. The ice cores say the circulation failed. The physics says a freshwater pulse could cause it to fail. The geology of the land surrounding the ice sheets holds the record of where that water was stored and how it moved. And there, in the record of the land, a lake enters the story. A lake so enormous it strains the usual frames of reference for what a lake is, how large a body of still water can be, how much fresh water can be stored behind a dam of ice and waiting to be released when the dam breaks. But that lake, and the routes its water took, and the disputed geography of the flood, is where the next part of the story lives. For now, the recording instruments have done their work. The ice has given its testimony. The mechanism is in place, the circuit understood. Too much fresh water, too suddenly arriving in the wrong part of the ocean, stalling the engine that kept the heat moving and holding the stall for 1,000 years. The cold was not in the end a mystery of physics. It was the consequence of an ocean being asked to do something it could not continue doing once the water arriving on its surface was no longer the kind of water it needed. And somewhere in Greenland, in a storage facility, climate-controlled to temperatures that keep the ancient ice from changing what it has held for 12,000 years, that testimony still exists. A cylinder of ice from a depth corresponding to 11,700 years ago, holding inside it the chemical signature of a world snapping back to warmth, the oxygen ratios climbing in the record of a decade, the dust falling away, the accumulation thickening as the moisture returns, the formally ratified boundary of our own geological epoch, a line in the ice that is the beginning of everything that has happened since. And below it, going back through the cold years and the cold layers, the long-held breath of the Younger Dryas, sealed there patiently, waiting to be read. And so we arrive at the water. Not the ice, the water. Because once you understand what the ice cores recorded, and once you accept the mechanism, the question that remains is the simplest and the most enormous. Where did enough fresh water come from to do all of that? Where did a volume of water sufficient to lower the surface salinity of a significant portion of the North Atlantic actually originate? And how did it get there fast enough to stall the conveyor, not gradually like a slow leak, but suddenly like a valve thrown? The answer has a name, it has a geography, and the scale of it, once you let it settle in your mind, is one of those facts about the ancient Earth that simply refuses to feel proportionate to anything in ordinary experience. Glacial Lake Agassiz. It is worth staying with that name for a moment because the thing it refers to is not, strictly speaking, a lake in any sense that the word lake usually conjures. When you hear the word lake, you may think of something you can see across, something bounded by shorelines you can walk along, something with a far bank, even if you need binoculars to find it. Lake Agassiz was not that kind of thing. At its greatest extent, Lake Agassiz was larger than all of the modern Great Lakes combined. Every single one of them, Superior, Michigan, Huron, Erie, Ontario, pooled together into one body of water, would not have matched it. It sprawled across what is now central and southern Canada, covering parts of what we call Manitoba, Saskatchewan, Ontario, and reaching into what is now the northern United States, into Minnesota, into North Dakota, in a vast, shallow, cold inland sea whose shores were not hills and forests, but the active margins of the Laurentide Ice Sheet itself. The dam that held it was not stone. It was not a concrete wall or a ridge of bedrock. It was glacial ice, enormous and slow-moving, pressing down against the land and holding the meltwater in behind it, the way a hand might hold water in a cupped palm. The Laurentide Ice Sheet, at its maximum, had covered enormous portions of North America under a weight of ice that was, in some places, kilometers thick. And as the world warmed out of the last glacial maximum, as the Bölling-Allerud interstadial brought the temperature climbing and the ice margin retreating, all of that ice was melting from its edges, melting in quantities that are genuinely difficult to reason about from ordinary life. A cubic kilometer of ice, melted, becomes a cubic kilometer of fresh water. The Laurentide Ice Sheet contained, at its peak, vastly more than that. And as it retreated, as the ice that had formerly covered the land withdrew northward, it left behind it a landscape scraped down to bedrock and depression, and where the retreating ice still pressed against the southern lowlands, it created a reservoir, a container. The water had nowhere to go as long as the ice held it in. So it pooled, it deepened, it widened, it became, over centuries and millennia, Lake Agassiz. Think of it this way. If you have ever seen a puddle form behind a temporary dam, a child's sandcastle on a beach, a ridge of packed earth across a sidewalk, you understand the principle, even if the scale is so different as to make the analogy feel slightly absurd. The water cannot drain away because something is blocking it. It fills to the level of the obstruction. It stays there as long as the obstruction holds. And when the obstruction fails, the water leaves, quickly. The question that paleoclimatologists and geologists have spent decades trying to answer is where the water went when the dam, or some portion of it, finally gave way. And the answer is not as settled as you might expect, because the drainage routes available to the water emptying out of Lake Agassiz were multiple, and the geological evidence for which of them carried the critical pulse of fresh water into the ocean is, depending on which research group you ask, subject to interpretation. The traditional model, the one that dominated for a long time, sends the water east and south, the St. Lawrence, that great river system draining the eastern interior of the continent, emptying into the Gulf of St. Lawrence and from there into the North Atlantic. It is a compelling route because it is a large route, because it connects the interior of the continent to the ocean in a direct and well-understood way, and because the geometry of it makes intuitive sense. If Lake Agassiz were to overtop or breach its ice dam along its eastern margin, water would naturally flow down the slope toward the St. Lawrence Basin. The St. Lawrence would carry it to the sea, and the sea it would reach would be precisely the North Atlantic, which is exactly where fresh water would need to arrive to suppress the deep water formation in the Norwegian and Labrador seas that the epoch depends on. There is geological evidence that this happened. There are sedimentary signatures in the St. Lawrence system that speak to very high flow events, and, for a time, the eastern drainage route was the standard explanation, the one you would find in textbooks and review papers without any particular qualification. But the story, as it so often does in the detailed history of the Earth, turned out to be more complicated than that. Because another route was proposed, one that sends the water not east, but northwest. Not toward the St. Lawrence, but toward the Mackenzie River system, into the Arctic Ocean. The work associated with researchers like Tarasov and Peltier using ice sheet modeling alongside the geological record raised the possibility, and in some versions of the argument, the strong probability, that the critical pulse of fresh water from Lake Agassiz drained not through the St. Lawrence at all, but northwestward, through what is now the Mackenzie River drainage, into the Arctic Ocean. From the Arctic, connected to the North Atlantic via the currents and exchanges of the high polar seas, this fresh water could still have reached the deep water formation regions. But the route is longer, the geometry less immediately obvious, and the geological evidence for it is in some respects harder to trace. Why does this matter? Why does the direction of the outflow from a lake that no longer exists matter enough that researchers are still debating it? It matters because if you want to understand the mechanism with any precision, you need to know where the fresh water entered the system. The epoch is not equally sensitive to fresh water arriving everywhere in the North Atlantic. Deep water formation is concentrated in particular regions, the Norwegian Sea, the Labrador Sea, where the specific combination of temperature, salinity, and density allows surface water to sink in sufficient quantities to drive the overturning. Fresh water arriving at different points would have different efficiencies, different lags, different consequences for the pattern of the shutdown. Knowing the route is not academic detail, it is a piece of the physical mechanism itself. And the honest answer, as of the evidence available, is that the exact route remains disputed. The geological record of pro-glacial lake drainages is fragmentary by nature. The floods themselves, by their violence and volume, scour away some of the very evidence they might otherwise leave behind. What seems clear is that Lake Agassiz drained, that it drained in ways that were catastrophic by any ordinary measure of catastrophe, and that fresh water from that drainage reached the North Atlantic system, by the St. Lawrence, or by the Mackenzie, or by some combination of both, in quantities sufficient to weaken or disrupt the epoch. The precise path is the unresolved piece, and that unresolved piece is itself a reminder of how the deep past presents itself to us, not as a clean narrative with every mechanism labeled and every connection confirmed, but as a record that is rich in places and frustratingly silent in others, where the floods erased the evidence of the floods. Now, here it is necessary to make a careful distinction, because the story of the ancient Earth in this period contains more than one large and dramatic freshwater event, and they are easy to confuse because the names are similar and the episodes feel related. And in a general sense they are related, being born from the same ice sheets and the same warming, but they are not the same event, and they did not produce the same consequences. Meltwater Pulse 1A. This is a separate episode earlier, distinct in both its timing and its effect. Meltwater Pulse 1A occurred roughly 14,600 years ago, that is, during the warming of the Berling-Allerud interstadial, before the Younger Dryas cold reversal began. It is visible in the sea level record as a dramatic and rapid rise. Global sea level climbed on the order of 15 to 20 meters over just a few centuries. That is an extraordinary amount of water added to the oceans in a very short time. 15 to 20 meters of global sea level represents an almost incomprehensible volume of ice that was no longer ice. Coastlines that had been dry land were submerged. River estuaries that had been river valleys became open water. Shallow continental shelves that had been exposed land during the glacial maximum were flooded. Meltwater Pulse 1A is associated with the warming of that earlier period. It is one of the signals in the geological record of how rapidly the ice sheets were capable of shedding mass when the climate shifted. And it establishes something important, that the Laurentide Ice Sheet and the other great ice sheets of the glacial maximum were not monolithic and stable structures that declined only slowly and predictably. They were capable of delivering fresh water to the oceans in sudden, massive pulses, not dribbles, not gradual trickles, but volumes large enough to register in the global sea level record across a span of centuries. But Meltwater Pulse 1A is not the trigger of the Younger Dryas. This is important enough to say twice. The two events are temporally distinct. Meltwater Pulse 1A happened during the warming. The Younger Dryas happened after it, roughly 12,900 years ago as a cold reversal in a world that was already considerably warmer than the glacial maximum. The fresh water associated with the Younger Dryas onset is not the same fresh water as meltwater pulse 1a. They are episodes from the same general story of deglaciation, but they are different chapters with different sources and different consequences, and conflating them is the kind of error that seems easy to avoid once it is pointed out, but that is surprisingly common in popular accounts of this period. What meltwater pulse 1a does tell us is that the world had the raw material for the Younger Dryas. It tells us that the ice sheets were melting in the Bölling-Allerud, that the meltwater was going somewhere, that sea level was rising, and that the reservoirs and lakes and impoundments along the ice margins, including, eventually, Lake Agassiz, were accumulating water that would, sooner or later, need to go somewhere. The warm period charged the system. The Younger Dryas was the consequence of the system discharging, and when that discharge came, when the fresh water entered the North Atlantic in sufficient quantity to weaken the overturning circulation, the cold did not fall evenly across the world. This is one of the aspects of the Younger Dryas that is easy to miss in a straightforward telling, one of the places where the real story is more complicated and more interesting than the simplified version, and also, in a certain sense, more strange. The Younger Dryas was not a global cold snap in the sense that every part of the Earth cooled together and equally. It was a Northern Hemisphere event, and within the Northern Hemisphere, it was strongest around the North Atlantic and its immediate margins: Europe, Greenland, the North Atlantic itself. These are where the signal is sharpest, where the temperatures dropped most severely, where the pollen record shows tundra plants returning to landscapes that had begun to fill with forest, where the glaciers re-advanced. But the Southern Hemisphere tells a different story, and the reason for that is a phenomenon that goes by the name of the bipolar seesaw. The bipolar seesaw is a consequence of the way the ocean circulation connects the hemispheres. When the epoch, the Atlantic Meridional overturning circulation, carries warm tropical surface water northward, that heat is delivered to the North Atlantic and its surrounding lands. But something else happens simultaneously. The southward flowing deep return current of the ocean, the cold, dense water sinking in the north and flowing south along the deep ocean floor, is also part of this exchange. When the overturning weakens, when the fresh meltwater suppresses the sinking in the north, the southward transport of cold, deep water also weakens. The net effect is that heat, which would otherwise have been pumped north and released into the North Atlantic atmosphere, accumulates instead in the Southern Ocean. It is not lost, it is redistributed. The South, broadly speaking, does not cool. When the North cools through an epoch slowdown, it warms, or at least it does not cool in the same way. The Antarctic ice cores do not show a Younger Dryas cold event mirroring Greenland. They show something more subtle and in some respects opposite, a slight warming tendency during the interval, or at minimum a muted and divergent signal, rather than the sharp, deep cold registered in Greenland. This is the seesaw in action. The two poles, swinging in opposite directions connected by the ocean's slow circulation, balancing the planet's heat in a way that is counterintuitive if you think of climate change as something that happens uniformly everywhere at once. And the seesaw extends in more attenuated and complex ways beyond the poles themselves. The Younger Dryas disrupted the atmospheric circulation of the tropics. The great monsoon systems of the world, the Indian monsoon, the West African monsoon, the East Asian monsoon, are driven in part by temperature gradients between the ocean and the land, and those gradients were altered by the changes in ocean heat transport during the Younger Dryas. The record from lake sediments and cave stalagmites across Asia and South America, from the oxygen isotope ratios locked in ancient cave minerals, from the pollen and organic matter preserved in ancient lake beds, shows that the tropical rain belts were displaced and disrupted during this interval. Monsoons weakened in some regions, aridity intensified in others. The Younger Dryas was felt in these indirect and attenuated ways in landscapes very far from Greenland and the North Atlantic. India, during the Younger Dryas, experienced what the proxy record suggests was a weakening of the monsoon system. The rains that ordinarily sweep in from the Indian Ocean during the summer months were diminished. This mattered to the ecological communities of the region, the plant communities, the animal populations, in ways that were not the same as the direct cold of the North Atlantic, but were real disruptions nonetheless. The disruption traveled through the atmosphere, through the temperature gradients that organized the tropical rain belts, rather than through the ocean itself. In China and across East Asia, similar signals appear in the cave record. Stalagmites in caves in southern China grow in annual layers, and the oxygen isotope ratio in each layer encodes information about the source and amount of the rain that fell on the limestone above the cave and percolated down to feed the calcite growth. During the Younger Dryas, those records show a shift that corresponds to a weakened East Asian monsoon. The oxygen ratios change. The rain diminished. The record of the cold in Greenland is legible in this indirect and translated form in the chemistry of cave minerals in subtropical Asia. South America tells a related story. Lake sediments from the Andes and from the Amazon basin record changes in precipitation and vegetation that correspond to this interval. The specific patterns differ by region. The Younger Dryas did not produce a single simple response across the whole continent, but the broad fingerprint of a disrupted tropical circulation is there. A system whose heat distribution engine had been partially stalled and whose atmospheric consequences spread far beyond the North Atlantic that was the center of the disruption. Even the African continent felt it. The West African monsoon, the rain system that governs much of the Sahel and the sub-Saharan zone, shows a weakening during the Younger Dryas in the sediment and pollen records from West African lakes and marine cores off the African coast. The Green Sahara, which would eventually flourish in the warmer and wetter conditions of the early Holocene, was not fully established during this cold interval. The moisture that would eventually transform the Sahara into a landscape of lakes and grasslands was, during the Younger Dryas, diminished. This unevenness, the deep cold of the North Atlantic margins, the muted or opposite signal in Antarctica, the weakened monsoons in the tropics, the aridity in some regions, and the altered precipitation in others, is not a complication that makes the Younger Dryas harder to understand. It is, in fact, the mechanism at work. The epoch does not just warm the North Atlantic, it is part of a global system of heat and moisture distribution. When that circulation weakens, the consequences are felt not just where the heat normally arrives, the North Atlantic, Northern Europe, the lands bordering Greenland's cold seas, but wherever the normal distribution was organized around it. The disruption radiates outward from its point of origin, diminishing with distance, but never fully disappearing before it crosses hemispheres. And in Europe, the story was the most direct and the most dramatic. Landscapes that had spent the Bölling Allerud interstadial beginning to fill with trees, birch, pine, the first tentative advance of the forest that would eventually cover much of temperate Europe, reverted. The trees died back or retreated south. The tundra returned. Dryas octopetala, that small white-flowered plant with its 8-petaled blooms and its tolerance for cold, thin soils, was not retreating to a few mountain redoubts. It was returning to lowland Europe, to lake shores in Denmark and Germany and Scotland, to landscapes that had briefly looked like they might be done with glacial cold. You can read this in the pollen record in a way that is almost eerie in its specificity. Layer by layer in the sediment cores from European lakes, the pollen of woodland trees diminishes. The birch and pine, which had been increasing, thin out. And the pollen of the tundra plants, the dryas, the grasses of the Arctic, the sedges of cold and open ground, rises again. It is a stratigraphic reversal, a layer of sediment that looks like the record of a slowly warming, increasingly forested landscape, and then, above it, a layer that looks like the record of the cold returning. And then, after the Younger Dryas, the woodland pollen climbing back again, more completely and more permanently, into the warmer Holocene. The pollen record is not just evidence, it is a portrait of real plants in real landscapes responding to real temperatures. The Dryas octopetala that gives the period its name was not a metaphor or a marker. It was a flower that grew, that spread its roots through the thin mineral soils of cold Europe, that opened its white petals to a sun that was bright but no longer warm enough to keep the glaciers at bay, that produced its pollen and released it into the air of a world that had gone cold again. And when that pollen settled onto the surface of a lake and drifted down through the water and buried itself in the accumulating silt of the lake bed, it became part of the record that thousands of years later, scientists would pull up in a core and read. The Younger Dryas in the pollen record of European lakes is not an abstraction. It is a flower. A small, cold-tolerant flower that came back when the cold came back, and whose pollen, buried in the mud, has been waiting 12,000 years to tell the story. And the cold across Europe was not mild. This was not a modest setback in the warming, not a slight slackening of the pace of recovery. The Greenland ice cores, which have given us the clearest temperature record of the event, suggest that temperatures in and around Greenland itself dropped dramatically from the Bølling-Allerød levels. Europe, which does not have the same direct ice core record but can be reconstructed from multiple proxy sources, pollen, beetles, lake chemistry, soil development, experienced a return to conditions that resembled the cold of the late glacial period more closely than the warmer interval that had preceded the reversal. Not identical to the full depth of the last glacial maximum, which had ended several thousand years before, but genuinely cold. Cold enough that glaciers re-advanced in mountain regions, cold enough that permafrost, with the permanently frozen ground of Arctic climates, returned to areas of northern Europe that had begun to thaw, cold enough that the human cultures of the late glacial, already adapted to the difficult conditions of the Ice Age world, had to adapt again to a landscape that the warming had briefly softened before taking it away. Britain, at this time, was not yet an island. The land that would become the British Isles was still connected to continental Europe across what would later become the North Sea and the English Channel. The sea level had risen since the glacial maximum, but had not yet risen enough to cut the land bridge. And across that continuous landscape, the cold of the Younger Dryas settled. The tundra that the Bølling-Allerød warming had begun to push northward returned southward. The periglacial conditions, the freeze-thaw cycles, the ice wedge polygons forming in the ground, the solifluction lobes of material moving slowly downhill under the force of ice, are visible in the geological record of Britain from this period. A landscape that had begun to look as though the cold was behind it found the cold had returned. Scandinavia, which had been deglaciated in its southern portions during the Bølling-Allerød, saw glaciers re-advance. The Scandinavian ice sheet, already in retreat, pushed back. The fjords and valleys that had opened began to fill again with ice. The dating of these re-advances, matched to the chronology of the Younger Dryas, is one of the ways the event is documented on the ground, in the landscape itself, not just in cores. The cold fell across the northern world and reached into the tropics in its attenuated atmospheric form, and it held for approximately 1,200 years. a duration that is difficult to feel the full weight of when you read it as a number. But 1,200 years is longer than the gap between us and the Norman conquest of England in 1066. It is longer than the period between the fall of the Western Roman Empire and the present day, depending on how you count. It is not a brief episode. It is a sustained cold maintained by the weakened epoch for generation after generation after generation of every creature that lived through it, or failed to. And the living world during those 1,200 years is part of the story. Not just the plants, not just the pollen, but the animals, the large animals, the extraordinary collection of megafauna that had inhabited the Pleistocene world, and that, during this interval, were diminishing toward extinction, or in some cases had already largely disappeared. But that is the question that the next part of this story lives inside. The creatures, the cultures, the animals that had endured the full depth of the glacial maximum and survived the warming only to find themselves in the world of the Younger Dryas. And the people, the Clovis people, whose distinctive tools and whose story ends or transforms or disappears from the record at almost exactly the moment the cold returned. For now, hold the geography. The lake that was larger than all the Great Lakes combined, holding its cold fresh water behind a wall of ice. The disputed routes through which that water found the sea, east by the St. Lawrence, or northwest by the Mackenzie, or by some combination of both that the geological record has not yet fully resolved. The bipolar seesaw tipping its southern hemisphere down into relative warmth as the north shivered, the monsoons diminishing across Asia and Africa, the tundra flowers returning to European lake shores, the cold held steadily in place by a stalled ocean, spreading its consequences unevenly across a world that had thought the Ice Age was behind it. The water came from the ice, and the cold came from the water. And the world that emerged from those 1,200 years, when the cold finally released its hold, would emerge into a warmth that came as quickly as the cold had come, and would be as difficult to explain as the cold itself, an ending as abrupt as the beginning, waiting just ahead in the story. And so the animals had been living through it all, long before the lake drained and the ocean stalled, long before the monsoons retreated and the tundra flowers returned to the lake shores of Europe. The great creatures of the Pleistocene had already been navigating a world in flux. They had come through the glacial maximum, that long, deep cold when the ice stood 2 miles high over what is now Quebec, and the sea level sat 120 meters below where it sits today. And they had survived it. The mammoths had followed the edges of the tundra and the grasslands. The mastodons had moved through the spruce forests of the northeast. The giant ground sloth had browsed in the middle of the continent, a creature so large that the word giant in its name is not an exaggeration, but a precise description. Some species reaching a body mass comparable to a small elephant, standing upright to reach foliage that nothing else could touch. The Smilodon, which most people call the saber-toothed cat, though it was not precisely a cat in the modern sense, had been hunting the mega herbivores across the grasslands of North America for thousands of years. The dire wolf had run in packs across the same landscapes where modern wolves would later run. The short-faced bear, arguably the largest terrestrial mammalian predator on the continent, had commanded the open ground. There was a glyptodon, an armadillo the size of a small car, its shell a dome of interlocking bone, moving slowly through the grasslands of what is now South America, and that lineage had extended into the southern edges of North America. The American horse, which most people do not realize went extinct on this continent, had been grazing the plains for millions of years. The American camel, too, not a dromedary or a Bactrian, but a distinct lineage that had evolved here, and eventually sent emigrants across the Bering Land Bridge westward, giving rise to the Old World camels while the original North American lines remained, and then, near the end of the Pleistocene, disappeared. All of them, every one of them, are gone now. Gone at roughly the same time in the broad geological sense, though the word roughly is doing a great deal of work in that sentence, and the exact timing of each extinction and the relationship between the timing and the cause is precisely where the argument lives. The extinctions are not in dispute. The fossil record is clear on the fact of them. What is disputed, what has been argued since the 1960s and is still argued today with considerable force, is why. And the Younger Dryas sits at the center of that argument like a piece of circumstantial evidence that everyone agrees is real and nobody can quite agree how to interpret. The three main frameworks that researchers have advanced are human overhunting, which the ecologist Paul Martin formalized as the overkill hypothesis in the 1960s, and which argues that the arrival of skilled human hunters into a fauna that had never co-evolved with such predators was sufficient to collapse populations that were already not large. Climate and vegetation upheaval, which includes the Younger Dryas cold and the associated disruption of the grassland and forest systems that these creatures depended upon, and disease, which is far harder to test from the fossil record, and which most researchers treat as a secondary possibility rather than a primary driver. Most of the current scientific literature, when pressed for a conclusion, lands somewhere in the vicinity of a combination: climate stress reducing populations and fragmenting habitats, with human hunting pressure finishing off what the cold had weakened. But the honest summary is that there is no single cause established beyond reasonable scientific debate, and researchers who have spent careers on this question continue to disagree about the relative weight of the factors. The Younger Dryas provides a plausible mechanism for the climate side of the argument: a return to near-glacial conditions over the span of decades, the grassland shifting, the spruce forests retreating or expanding depending on the region, the food systems of the mega-herbivores rearranging themselves just as human populations were increasing, is exactly the kind of disruption that could stress large mammals with slow reproductive rates, the kind of animals that take years to reach sexual maturity and produce only one offspring at a time. A mammoth does not recover a population the way a rabbit does. A giant ground sloth does not bounce back from a decade of food source disruption the way a small rodent might. Large body size, which is an advantage under many circumstances, becomes a vulnerability when conditions change faster than a slow reproducing species can adapt, and the timing does overlap. The broad window of the megafaunal extinctions in North America, not the extinction of every species on exactly the same day, but the general disappearance of the large Pleistocene fauna, does overlap with this period. With the Younger Dryas, with the arrival and expansion of human hunters. Both pressures were present simultaneously, and distinguishing their effects from the skeletal and stratigraphic record is genuinely difficult work. The overkill argument has some independent lines of support. Australia lost its megafauna considerably earlier, before the Younger Dryas, around the time of the earliest human arrival on that continent. Madagascar and the islands of the Pacific lost their large fauna much later, when humans arrived there, also before any relevant climate event. These patterns suggest that human arrival is a sufficient condition for megafaunal collapse in some circumstances, independent of the Younger Dryas entirely. But North America is not Australia, and the patterns are not perfectly analogous, and the climate disruption of the Younger Dryas was severe enough that it cannot simply be set aside as irrelevant. And then there is the Clovis question, which is tangled up with all of this in ways that are still being worked out. The Clovis people, or more precisely, the Clovis cultural tradition, are defined by a distinctive stone tool technology. The Clovis point is a fluted, bifacially worked projectile point, chipped from stone with a precision and a characteristic technique that is recognizable and distinctive across an enormous geographic range. Finding a Clovis point in a stratigraphic layer is finding a marker, a kind of timestamp for a particular cultural moment in the peopling of the Americas. And the Clovis horizon, the layer in the archaeological record where those points are found in abundance, ends at a time that roughly coincides with the onset of the Younger Dryas cold around 12,900 years ago. What this coincidence means is the dispute. One interpretation is cultural collapse. The Clovis people were large game hunters, particularly mammoth and mastodon hunters, and when the megafauna declined, whether from climate or overhunting or both, the specific ecological niche that the Clovis technology was optimized for collapsed with the animals. Without the large prey, the Clovis point, which is a large game hunting tool, becomes less useful. The culture that produced it fades. The other interpretation, and this is where many archaeologists now lean, is not collapse but transformation. The Folsom culture, which comes after the Clovis horizon in the North American record, shows a different but recognizably related stone tool tradition. The Folsom point is smaller, adapted to hunting the bison that remained after the megafauna disappeared. If you look at the trajectory from Clovis to Folsom, you can read it as an adaptation. The people continued, the animals they hunted changed, the tools changed with them. Not a disappearance, but a pivot. The word disappearance in the archaeological record is always partly an artifact of what gets preserved and what gets found. A culture that shifts from mammoth hunting to bison hunting and adjusts its toolkit accordingly does not leave a visible gap in the record, it leaves a transition. Whether the Clovis to Folsom transition was catastrophic or gradual, traumatic or orderly, is a question the stones themselves cannot fully answer. What can be said with some confidence is this: the coincidence of the Younger Dryas onset, the megafauna timeline, and the Clovis horizon is real and not manufactured. Three things that are each independently documented ended or transformed at roughly the same time. Whether they caused each other, or were all caused by something else, or were independent events that happened to overlap, this is where the science remains open. And then, into this already complicated picture, in roughly 2007, a group of researchers led by Richard Firestone, Alan West, and James Kennett proposed something considerably more dramatic. They proposed that all of it, the cooling, the megafauna, the Clovis collapse, had a single triggering cause, a cosmic impact or airburst event over the Laurentide Ice Sheet at or near the onset of the Younger Dryas, roughly 12,900 years ago. A fragmenting comet or asteroid, they argued, exploded over or struck the ice, releasing an enormous amount of energy, triggering catastrophic meltwater flooding that shut down the epoch, causing widespread biomass burning across North America, and simultaneously killing or fatally stressing the large mammals and disrupting the Clovis people. This is the Younger Dryas impact hypothesis, and it deserves to be presented honestly, which means presenting it as neither confirmed fact nor obvious nonsense. It is a genuine scientific hypothesis advanced by researchers with credentials and published in peer-reviewed literature, and it has generated an enormous amount of subsequent research, much of it aimed at testing whether the proposed physical evidence is real. The physical evidence the hypothesis points to is a layer, the Younger Dryas boundary layer, often called the YDB layer, which the researchers report finding at dozens of sites across North America, Europe, and elsewhere, all dating to approximately the same moment. Within this layer, they report several things: elevated concentrations of platinum, which is rare in the Earth's crust, but found in higher concentrations in extraterrestrial objects, magnetic microspherules, which are tiny spherical particles of iron that can form under conditions of extreme heat and rapid cooling, as in an impact or airburst event, evidence of carbon consistent with widespread burning, and what the researchers describe as nanodiamonds, cubic and hexagonal diamond structures at the nanoscale, which they argue can only form under conditions of extreme pressure and temperature, such as a cosmic impact. A platinum spike in the Younger Dryas boundary layer has been reported in Greenland ice cores and at multiple terrestrial sites. This is one of the more reproducible of the claimed markers, and its presence is not universally dismissed. Platinum is genuinely anomalous in the record at that time. But the mainstream response to the broader hypothesis has been largely skeptical, and the skepticism is grounded in specific technical objections that are worth understanding. Multiple independent research teams, not the same team retesting their own work, but different groups in different laboratories with different methods, have attempted to reproduce the key markers and have not consistently found them. Some of the proposed nanodiamonds have been challenged as misidentified mineral structures that can form through ordinary geological processes. The dating of the charcoal and burning signals across the proposed sites has been disputed, with critics arguing that the burning evidence is not synchronous, that fires happened at different times at different sites and were not part of a single event. And the microspherules, while present in some samples, have been argued to originate from other processes, including industrial pollution in some cases and ordinary cosmic dust in others. The honest scientific summary as of the state of the evidence is this: the hypothesis has not been falsified in the sense of being decisively proven wrong, but the burden of proof for an extraordinary claim has not been met. The mainstream paleoclimate community does not accept the impact hypothesis as the cause of the Younger Dryas. The mechanism most strongly supported by the physical evidence remains the meltwater-driven epoch disruption, the fresh water shutting down the ocean's heat conveyor, as the earlier parts of this story have described. Crucially, and this is a point worth sitting with, even the proponents of the impact hypothesis generally accept that an epoch disruption would still be the proximate climatic mechanism for the cooling itself. The impact, in their version of events, is the trigger that caused the catastrophic meltwater release. The actual chain of events that followed, the fresh water, the stalled ocean, the starved North Atlantic, the cooling, is largely the same in both stories. The dispute is not about whether the epoch shutdown explains the cooling. It is about whether a cosmic impact explains the meltwater, or whether the meltwater accumulated through the ordinary dynamics of glacial melting and ice dam failure. And so the Younger Dryas boundary layer sits in the record of the platinum anomaly, the disputed nanodiamonds, the microspherules, and the debate continues. This is not a case where one side is obviously right and the other obviously wrong. It is a case where the evidence is genuinely ambiguous, where the interpretation depends on techniques and dating methods that are themselves contested, and where researchers who are serious and capable disagree. That is how science often actually works, particularly when dealing with events that happened nearly 13,000 years ago and left their signatures in layers of sediment and ice that have been compressing and altering ever since. The one thing that should be resisted, and it is worth saying this clearly in a culture that sometimes treats ancient mysteries as an invitation to import uncritical certainty from outside the scientific record, is the temptation to use the genuine uncertainty of this debate as a license for claims that the evidence does not support. The Younger Dryas impact hypothesis is not a covert confirmation of lost civilizations, not a secret that mainstream science is hiding, not the explanation for Atlantis. It is a specific, testable scientific claim about a cosmic event at a specific time, and it is being tested by the methods that testing requires. The uncertainty is real, but it belongs to the hypothesis as it stands, not to a larger story layered on top of it. And then, after all of this, after the cooling that came in decades, after the 1,200 years of stalled ocean and tundra flowers and diminished monsoons and a changed world, the Younger Dryas ended. It ended fast. Faster, in some respects, than it began. The Greenland ice cores, the N-drip core in particular, record the termination with an extraordinary precision because ice cores record the world year by year, layer by layer, and the transition is visible not as a gradual trend, but as a sharp line. At approximately 11,700 years before present, the record changes. The dust layers that had been thick during the cold, because a colder, drier, windier atmosphere carries more mineral dust, thin suddenly. The isotopic signature of the ice, which reflects the temperature of the atmosphere at the time the snow fell, shifts sharply. Precipitation rates, which had been reduced during the cold, increase, and the temperature implied by those isotopic signatures rises by on the order of 10 degrees Celsius. 10 degrees. Over what the ice core record suggests was a span of roughly a decade, perhaps a few decades at most. To put that in terms that are easier to hold, 10 degrees Celsius of warming across roughly 10 years is not a slow glide. It is not a trend that would be noticeable year by year, perhaps, but it is a transformation of a climate system at a pace that has no parallel in the era of human instrumental records. The world did not warm gradually out of the Younger Dryas the way you might warm gradually out of a cold room by edging closer to a fire. It lurched, it snapped. The ocean conveyor, for reasons that are understood in principle but whose precise triggering mechanism at the termination is still a matter of active research, resumed. The deep water began to sink again in the North Atlantic. The northward flow of tropical heat restarted, and the North Atlantic warmed, and the air warmed with it, and the ice cores recorded the whole transformation in layers thin enough to count on your fingers, the formally defined base of the Holocene epoch, the boundary between the geological past and the age we currently live in, is that transition layer in the NGRIP ice core, not a date on a calendar, not a moment anyone was present for, a specific layer of ice pressed into the glacier of Greenland approximately 11,700 years ago, where the dust thins and the isotopes shift, and the world that had lurched back toward glacial cold finally, abruptly, and for reasons that remain imperfectly understood, lurched back toward warmth. The Holocene is what followed. The several thousand years of relatively stable warmth, warmer than the glacial maximum, warmer than the Younger Dryas, warmer than anything the preceding 100,000 years had offered, during which agriculture was invented, cities were built, writing was developed, the entire edifice of what we call human civilization was constructed. All of it happened within the unusually stable warmth that followed the Younger Dryas termination. The ice retreated. The forests advanced. The sea level rose to roughly its current position, and the human populations that had survived the cold and the disruption of the Younger Dryas expanded into a world that was, by geological standards, remarkably hospitable, none of which was inevitable. That is one of the things the Younger Dryas teaches. The warmth that made civilization possible was preceded by 1,200 years, when that warmth was interrupted, reversed, apparently ended. The world that emerged from the glacial maximum did not simply continue warming along a smooth curve toward the present. It lurched backward first, dramatically, in a way that no one living through it could have understood or predicted. And then it lurched forward again, even more dramatically, into the conditions that made everything that came after possible. The modern relevance of this story is real, and it should be approached carefully. The AMEA, the Atlantic Meridional Overturning Circulation, the same ocean conveyor whose disruption is the leading mechanism for the Younger Dryas cooling, is not a historical artifact. It is operating today. It is the same system that keeps winter temperatures in northwestern Europe milder than the same latitudes would otherwise be, the same system that moves heat northward from the tropical Atlantic, the same system that relies on the density difference between salty, warm, southward-flowing surface water and cold, dense, northward-sinking deep water, and the Greenland ice sheet is melting. Fresh water is entering the North Atlantic from Greenland's glaciers in volumes that are measured and tracked, and that are increasing. The question of whether this is enough, or will become enough, to measurably slow the epoch is not a hypothetical. It is a question that oceanographers and climate scientists are actively investigating with mooring arrays and float networks and climate models. The evidence from the current instrumental record suggests that the epoch has weakened somewhat over the past several decades, though the precise magnitude of that weakening and its causes are still being refined. What the Younger Dryas establishes beyond any doubt is that the epoch is capable of dramatic, fast state changes. That is not a prediction of what will happen, it is a demonstration of what is physically possible. The climate system can reorganize faster than we sometimes assume. The Younger Dryas is the proof of concept. Whether the current rate of Greenland melt approaches the threshold that would trigger such a reorganization is a different and open question, and the honest answer is that the threshold itself is not known with precision. But the Younger Dryas is the reason this question is taken seriously. Without it, without the physical evidence preserved in ice and sediment that the epoch actually has switched states rapidly within the natural range of the Earth's climate history, the possibility might seem theoretical. With it, the possibility is documented. The precedent exists, the mechanism is not hypothetical, and the planet's own meltwater has, at least once in the record we can read, been the instrument of a dramatic reversal. That is the thing the Younger Dryas teaches most quietly, if you let the full shape of it settle. It is not a story about cold. It is not a story about mammoths or Clovis points or even about a disputed comet crossing the ancient sky. It is a story about how a warming world sabotaged its own warming. About how the very process of melting, the release of the vast water stored in ice over the long glacial maximum, generated the conditions that temporarily reversed the warming and plunged the Northern Hemisphere back toward the cold it was escaping. The meltwater that was the product of warming became the cause of cooling. The system turned against itself, and then, after 1,200 years, whatever equilibrium had held the cold in place, whatever balance of fresh water and circulation and heat transport had kept the epoch suppressed, that balance shifted again. The fresh water was diluted or dispersed, or the ocean's internal dynamics crossed some threshold that the climate record marks clearly, but that the models have not yet reproduced with certainty. And the conveyor restarted, and the warmth returned, at a speed that is, even after all you have heard, still difficult to fully absorb. 10 degrees Celsius, roughly a decade. There is a small Arctic flower called Dryas octopetala, the mountain avens, white-petaled, with a yellow center, growing in the rocky ground above the tree line and in the tundra margins where the cold has kept the trees from advancing. This flower's pollen, buried in the mud at the bottom of European lakes during the cold phases, is how the Younger Dryas was first recognized. The lakebed layers that show the pollen returning are the original archive. The flower did not know it was leaving a record. It simply grew where the cold allowed it to grow and shed its pollen into the wind, and the wind carried the pollen over the water, and the pollen sank, and the centuries of sediment covered it, and thousands of years later, scientists with long coring tubes pulled up columns of that mud and read the layers backward in time, and there it was, the return of the cold-tolerant flower, announcing the cold's return as clearly as any instrument. There is something worth holding in that image. An entire interval of climate history, 1,200 years of cold that interrupted the end of the Ice Age, that possibly contributed to the extinction of the woolly mammoth and the dire wolf and the American horse, that disrupted the Clovis people and altered the monsoons of Asia and the rainfall of South America and left tundra flowers on the shores of European lakes. All of it announced and remembered by pollen, by something that small, something that required no technology to record, only the slow patience of sediment and the curiosity of people who thought to look. The ice cores in Greenland preserve the same interval in far more detail. Layer by layer, year by year, the dust and the isotopes and the chemistry of the ancient air pressed into ice that has been there since before any of the civilizations we call ancient. The GISP2 core and the N-grip core and the grip core, drilled from the surface of the Greenland ice sheet, pulled up in cylinders of compressed time, hold in them the Younger Dryas and its termination, and everything before and after it, available to be read by anyone with the right instruments and the patience to look carefully. A single layer in that ice is the defined base of the Holocene. The current epoch began in a line of ice that you could hold, in a sense, in your hands, and all of it, the cooling and the cold and the ending and the warming that followed, happened to a world that had people in it. Not many people, by modern standards. Not people with writing or cities or calendars that would have recorded the event directly, but people nonetheless living through a change they could not name or explain or have any reason to expect, watching the cold return to a world that had seemed to be warming, hunting animals that were, in that same interval, beginning to disappear. The Clovis people chipping their distinctive points from stone in a world of very large prey that would not much longer be there. The late glacial peoples of Europe watching the tundra return to forests that had recently advanced. None of them knowing that the cold would last 1,200 years. None of them knowing that it would end. None of them knowing that the warmth that returned would be the warmth inside which everything that followed would be built. They lived through it. They came out the other side, or they did not, and others came through them, descended, adapted, transformed into the world that the Holocene made possible. The Younger Dryas was not the end of the human story. It was, in a sense, one of its stranger and more consequential chapters. The cold that should not have happened in the middle of the warming that was supposed to be ending the Ice Age, that lasted long enough to reshape a world, and then ended fast enough to leave scientists still asking why. The questions are not all answered. The drainage route of Glacial Lake Agassiz, whether the water went east or northwest or both, has not been definitively settled. The relative weight of climate and human hunting in the megafaunal extinctions has not been established beyond dispute. The Younger Dryas boundary layer and its platinum and its contested nanodiamonds and microspherules remain in the record, still being tested, still being argued over by people who disagree in good faith. The precise threshold at which the epoch switched off and the mechanism by which it switched back on at the termination have not been reproduced in full by any climate model. And the ending, that 10-degree warming in roughly a decade, visible in a single archived glacier on an island in the North Atlantic, still carries a quality of astonishment that does not fade with familiarity. This is a story that ends without a neat answer because the world itself did not finish resolving the questions it posed. The cold came, it stayed, it left. And it left behind traces in the ice and the mud and the stone that we are still reading, still learning to read, still finding new ways to misread and then correct ourselves and read again. That is how knowledge of something this old and this complex accumulates, not in a single revelation, but in the slow layering of evidence and argument and correction, the way sediment layers itself on a lake bed, year by year, patient and without announcement, waiting for someone to pull it up and look. Somewhere right now, a core of Greenland ice is sitting in a freezer in a laboratory, its layers being measured in a light that did not exist when the snow that formed them fell. The mountain Avens is probably flowering somewhere above the tree line, small and white-petaled, indifferent to what its pollen once recorded. The Atlantic is moving its water in the great slow loop that it has moved in for thousands of years, carrying heat northward, sinking in the cold, returning south in the deep dark, the same circulation that once stalled and plunged a hemisphere back toward the cold and then, in a decade, restarted and let the warmth return. The world that nearly unwarmed did not stay unwarmed. That is not nothing. And the warmth that came back, when it came faster than anything in the instrumental record has since approached. That is also not nothing. Both facts sit together in the ice, and the reversal and the recovery, and they do not resolve into a comfortable lesson. They sit as facts, as evidence, as the record of a planet that can change faster than we sometimes expect, and that has, at least once in the memory of its own ice, turned the products of its warming against the warming itself. That is where the story leaves you, not with certainty, not with a cause fully established and a culprit named and a lesson extracted and filed away, but with the image of something very large and very strange that happened to this world a very long time ago and left its signature in places small enough to miss. A pollen grain, an ice layer, a line of dust, if you did not know to look. If this slow journey into the deep past has been a companionable one, if these old events and their quiet traces have given you something to think about on the way to sleep or something to carry into whatever comes next, then there are more stories here of the same careful and unhurried kind waiting for whenever you want them. And if you feel moved to share where in the world you are listening from tonight, I would genuinely like to know. The comments are there, and I read them. Lecture's over. Even the professor sleeps. Good night.